Okay, students, so on this clip we're going to be going over two examples on how to calculate exponential growth and decay. Um, Before we start, let's do a real quick recap of the formulas that we're going to be using. Okay, I'm going to organize them using the matrix. So let's generate the matrix real quick. So on the leftmost column, I'm going to be separating them into two categories. The first one will be growth, and the second will be decay. Okay, so we have growth and decay. All right. Another word for another terminology for decay is depreciation. I think depreciation. All right. Know that for decay, for growth, we're going up, quantities are increasing, or size is increasing, and then for decay, we're going down, or amount is decreasing. Okay. All right. There are two kinds. We can further divide these into two groups. So let's divvy our grid into two down the center. The first group I can divide growth and decay into is continuous. Okay, continuous. And then the second group is discrete. Okay, continuous and discrete. Now, for continuous, it could be either of the form y equals ae raised to the kt, or y equals ae to the rt. Okay, that's for our continuous growth. For continuous decay, it's very similar, but it's just y equals ae to the negative kt, or y equals ae to the negative rt. So the only difference here is the sign. The growth constant here is negated, it's positive, and the decay constant here is negative. The growth rate here is positive, and the growth rate here is negative, all right? For discrete growth, we're going to use the model y equals a times 1 plus r raised to the t. Okay, then for decay, we're going to use the formula y equals a times 1 minus r to the t. You can see that these two models are really similar. The only difference is the sign and the center switch. You always have negative before the rate for decay and positive before the rate, as you can see here, for growth. All right. Okay. Now, what do each variable mean? The a's basically represents the initial amount. The initial amount is your a. Okay. And then r, where we have r, is the growth or decay rate. Okay, growth or decay rate. And then for k is known as the decay or growth constant. Growth constant. And y is the final amount. All right, y is the final amount. Now, in most cases, you have continuous. When you have continuous growth, this most cases has to do with scenarios where you're dealing with things such as radioactive substances, radioactivity, like carbon-14 or plutonium, or population growth. Okay. In most cases, these are the kind of problems that involves continuous growth. For discrete, it mainly has to do with business. All right, business, the business of investing or depreciation, anything that has to do with money. In most cases, you're gonna find yourself using these formulas. All right. So there you have it. Okay, now with these formulas in mind, let's go ahead and write down the instruction for the examples we're going to do. So the instructions are to solve each problem by first stating if the situation is growth or decay, um, or if it's discrete or continuous. Okay, let's make this and, because you're gonna have to do it. Is it growth or decay? And is it discrete or continuous? Okay, so after indicating the kind of behavior of the quantity of the model, then we're going to go ahead and state the formula. And the value of each component. Okay. All right. With that in mind, let's start with question number 1. Okay. Question number 1 is a problem on investing. Okay. As a problem on investing. So this is the problem. Jose is very rich. Jose invests $10,000 in a fund, that pays an annual interest of 15%, which is pretty good, once per year. Okay. Find the amount of time. It will take. Jose's investment to rise to $15,000. Okay. All right. Now let's go ahead and work this out. So for the instructions of these problems, we are first supposed to indicate if it's growth, decay, or discrete form or continuous. So in this problem, this is an interest. Okay, it's not a charge. This is interest, so it's going up. When he puts the money in this fund, he wants the value to go up, right? So every year they pay him 15% interest, so this is up, so his amount is growing. So this is clearly a growth situation. It's growth, and since it's per year, that means every year is not continuous, it's broken. So it's growth and it's discrete growth. Okay, it's discrete growth. Now, what model do we use for discrete growth? We're going to use the model y equals a times 1 plus r to the t. Okay, now let's state the value of each component. A is the initial amount. How much did Jose start with? He started with $10,000. What is the interest rate? Now, we're going to be really careful here. The interest rate is 15%. In numerical form, is 15% means over 100. Okay? So how do I convert this into decimal for easy computation? Well, I just put a decimal behind the 100 and a decimal behind the 15. Now move the decimal forward twice to get rid of the denominator, 1, 2, and move it in the numerator an equivalent number of times, 1, 2. Okay? So I'm going to have 0.15 over 1, which is just 0.15. So the growth rate is 0.15. So if you want to change your percentage into numerical form, you just simply move the decimal point forward twice. Okay, so be really careful with that. Now the time is how long it'll take Jose to have 15,000. Well, guess what? That's what we're looking for, so I have no idea. What's the final amount after the time has elapsed? The final amount, or the target amount, is $15,000. Okay, so what I'm going to do is I'm going to take all this information, input it into this nice model here, this formula, and then solve for t. Alright, let's go ahead and do it. So we're going to have, let me rewrite the formula here so we don't get confused. The formula is y equals a times 1 plus r to the t. So y is 15,000, so we have 15,000 equals, the initial amount is 10,000. 10,000 times 1 plus r is 0.15. T is the amount of time which we do not know, so it remains a variable t. Okay? The goal here is to isolate these exponents, t is power t. So first thing we're going to do is we're going to divide both sides by, we're going to first of all divide by 10,000, get rid of this coefficient, so divide both sides by 10,000. 10,000 on the left, 10,000 on the right. Okay, these divide out to 1, and in this case we can just divide out the zeros by 1,000, divide out. 15 over 10, we can divide both sides by 5. Okay, divide by 5 top and bottom. So on the left side, 15 divided by 5, oh wait, I didn't write this correctly, I gotta be careful with this. Divided by 5, so divide by 5, divide by 5. Remember, division does not commute, so the order matters. Alright, so 15 divided by 5, I have 3 over 2 equals 1 plus, well, 1 plus 0.5 plus 0.15 is simply 1.15, right? 1.15 raised to the t. Alright, now I need to power down this exponent. In order to power down any exponent, I need to have it written in logarithmic form. Okay, so I'm going to take the natural logarithm of both sides. The natural logarithm of the left side, 3 over 2, and the natural logarithm of the right side. Okay, why am I taking the natural logarithm of both sides? Well, that gives me the power to take advantage of one of the properties of the logarithm, which is a power property, that enables me to power down the exponent, so this power comes down. Alright, so we're going to have the natural logarithm of 3 over 2 equals t times the natural logarithm of 1.15. Alright, now that we've powered it down, we can simply isolate it by dividing by this constant right here. So I'm going to divide both sides by the natural logarithm of 1.15. By the left and right by a natural logarithm of 1.15. Alright, well, let me use a different color. So natural logarithm of 1.15. And on the left, divide by natural logarithm of 1.15. These divide out to 1. Using the reflexive property of equality, I'm going to have t equals the natural logarithm of 3 over 2 divided by the natural logarithm of 1.15. Okay? Now this is the exact answer, but this doesn't make any sense. Let's plug it into the calculator so that we can have a better idea as to how much time it takes, okay? Alright, so we have the natural logarithm of 3 divided by 2, close that, divided by the natural logarithm of 1.15. And our answer is 2.9, so roughly 2.9 years, almost 3 years. So t equals 2.9 years. Okay, now we have to state what this answer means. So what does this mean? It will take 2.9 years for Jose's investment to grow from 10,000 to $15,000. Okay, so I expect everyone to indicate this when you conclude after you finish doing your problems. Okay. All right. Now let's move on to question number 2. Question 2. This is a population problem. Population. Okay. So let's underline. You can write down what the situation is. This is has to do with a foreign planet. Let's go ahead and write down the description of the problem. It says the population growth model for planet Namek, is P equals 50e to the 0.012t. Okay, where t is the time in years. All right. In how many years? Will the population be 10,000? 10,000. All right. Okay. So let's go ahead and do the problem. So first thing, for the instructions of the problem, is we're supposed to describe it, right? So is it growth or decay? If you look at the growth rate right here, this is positive, right? So since it is positive, we know that the population is growing, okay? If this were negative, the growth rate, the factor of t, if this were negative, then we know that is decay, okay? So here we know that this is a growth scenario. Is it decay? Is it continuous or discontinuous? Is it continuous or discrete? Since there's no reference here to rate, and it's in the form e to that, if it's in this form, it's automatically a continuous situation. So this is growth and continuous. All right. You remember? Let's scroll up real quick. In the models we talked about, whenever it's of this form e to the, remember it's continuous. Okay. This is a representation for continuous growth, and then it has to be positive. The constant or growth rate have to be positive for it to be growth. Okay. And we can see that that's the case here. The growth rate is positive and it's in the form e to the, so we know that it's growth and it's continuous. Now, what is the formula that we're going to use? The formula that we're using here is y equals a e to the rt. Okay? Okay, now let's see what each component means. A is the initial amount. What is the initial amount? Well, let me write this model down here so we can compare them clearly and see what's going on. So I'm going to write it. I'm writing green. We have P equals 50 e to the 0.012t. So what is the number that comes before the e? That's what a is, right? So what number comes before e here? A is 50. So there were originally 50 people. 50 people on planet Namek to begin with. Okay. All right. Now, what's the growth rate? The growth rate here is 0.012. Notice that it is not in percent. It has already been converted to the numerical form. Okay, 0.012 is the same thing as 1.2%. Okay, so you leave it in this form, 0.012. And then the time, how long it takes to hit the target population of 10,000. We have no idea. It says how many years. That's what we're looking for, question mark. And then the final amount as P, Y is the same thing as P, okay? In this case, it's 10,000. When will we have 10,000 Namekians on planet Namek, starting from 50 using this growth rate and this model? That's what the question is asking. All right, let's go ahead and plug in our arguments into this equation and then compute what the time it will take is. Okay, so let me write the formula so we do not get thrown off. Equals AE to the RT. So Y is 10,000. Y is the same thing as P. 10,000 equals the initial amount A is 50. E to the growth rate is 0.012. Time we do not know, which is T. Okay. So we'll start off by getting rid of the 50. To do that, we'll just simply divide both sides by 50. Divide by 50. And then let's do that first. Divide by 50, divide by 50. This side it divides out. the 0 counts divided out. 5 goes into 1,200 times. 200 equals e to the 0.012t. Now I want to power down this exponent, this exponent right here. The property or the function that gives me the ability to do that is a natural logarithm or the log of functions. Okay, so what I'll do is I'm going to take the natural logarithm of both sides. So natural logarithm of 200 equals the natural logarithm of e to the 0.012t. Okay, why am I doing this? Well, this allows me to power down the exponent. Okay, so now written in logarithmic form, this can be brought, I can power this down. Okay, I can power this can be coming down right here. On the left side, I'm going to have the natural logarithm of 200 equals 0.012t times the natural logarithm of e. Okay. Alright, simplifying further, we'll have the natural logarithm of 200. But check this out. ln and e are inverses, so what happens? They neutralize each other out. ln of e is basically equal to 1, because we already took that down, so it's just 1. So we're going to have 1 times this is just 0.012t. Okay? Alright, times 1, if you times this by 1, it stays the same. So to finish this up, to get t by itself, we're going to divide both sides by 0.012 on the left, and on the right, 0.012. Okay? These two divide out. So we're going to have, using the reflexive property of equality, t equals the natural logarithm of 200 divided by 0.012. Okay? Alright, we're going to need the help of a calculator to compute this quotient. So let's call for calculators. So we're going to do the natural logarithm of 200 divided by 0.012. Okay? Enter 441. Alright, so t equals 441.53. Okay, so t equals 441.5. Okay, so what on earth does this mean? It means that it will take 441.53 years to two decimal places for the population of Namekians to grow from the original amount. From the original amount of what? What was the original amount? From 50 to the target amount of 10,000. Okay, that's a long time, almost 4 centuries. Okay. All right, so there you have it. So thanks so much for taking the time to watch this video. You can feel free to subscribe to my channel just by clicking up here. You can share this with your friends via Facebook or Twitter. More videos coming from MacPrU3L6b.com. Thanks again and have a wonderful day.